game. With near we'll fan the flame. Empowered minds rise and soar. Use your own AI. We'll explore. Help the future hand in hand in this tech-driven wonderland.
Okay, hello everyone. Welcome to the next episode of Near AI Office Hours. Today we have Alex Hicks from Ethereum Foundation, and it's going to be a very exciting topic about formal verification. Alex, you want to say a couple of words about yourself and the formal verification efforts at Ethereum?
Yeah, absolutely. Thanks for having me on. And what a great introduction song. I'd never heard it before. So a bit about myself. I joined the Ethereum Foundation in June this year, so I've only been here for a couple months. And my job description there is essentially to try and find ways to use formal verification and AI to make Ethereum more secure. And so one thing that we're particularly interested in at the moment is trying to formally verify these big general purpose RISC-V zero knowledge virtual machines. So we have a big project that we've launched with a kind of big $20 million budget over 2 years. There'll be a lot of grants and a lot of bounties associated with this, and a lot of work that will get done, and hopefully some good results so that at the end we can, people can use these and be sure that they're not going to lose all their money, amongst other things. And part of that in the AI angle there as well is whether we can figure out ways to use AI in the same way that AI has become very useful for programming in mainstream programming language like Python, Rust, or C++. And if we could get AI tooling to be as effective for maybe not proof generation in terms of formal proofs, but maybe for maintenance and maybe auto-formalizing specifications out of codes and comments and markdown files and things like this. So that's something that's very much on my radar as far as trying to apply AI. And another angle, which is the angle that I originally had in mind before joining the Ethereum Foundation and that I was thinking about a lot, was around kind of formal verification for AI, because all these models we have now are really complex, and you can kind of prompt them for whatever you want, and you'll always get some kind of answer. Trying to figure out whether the answer that you're getting is kind of correct in any sense or consistent with any kind of logic is something that's also a big interest of mine. Because if we're going to have, maybe kind of user-owned AIs, as Ilya would put it in one of his talks, then it seems to make sense that you'd like some assurance that what you're getting out of the AI is actually kind of aligned in any sense with what you actually want to get out of it.
Yeah, it's very exciting. And to give some background on our end, out of I think 12 people today at Near AI, 3 people are very big, are very into formal verification. We will and discuss it quite frequently, do some drills, but we don't use it actively yet. I think the focus of big Near AI projects right now is on other things. However, we might have some announcements that redacted. We will see. But I personally spend a lot of time with formal verification, and I run this project where I annotate a lot of data, and I'm working on annotating. I'm about to launch a project to annotate some formal verification data. So this is something you mentioned. How do we make models better at formal verification? So I'm about to launch some experiments in that area. And I guess the first question I have, which is around ZK-EVM. So I looked at the website. There's a website. It's verified-zkevm.org where people can find more detail. Something that is not, at least I didn't quite understand, is whether the goal is to prove the implementation of the ZK-EVM, or if the proof is to build the construction itself of the zero knowledge machinery, if the question makes sense.
Yeah. So it should really be both. Hopefully it should be both. And I think we've set ourselves for kind of 2-year timeline to do this. And I think we should be able to get both, because one thing that's missing at the moment is that you have these KVMs that exist that are now coming into production, and people are going to run, maybe rollups on these and a lot of other applications. So we want to make sure that they're nice and secure, and they're built on top of, RISC-V is at this point a fairly well understood ISO and it's fairly stable. If you're running a rollup on this for Ethereum, you've got the EVM. Maybe you could run some new applications on it as well and things like this. And for the EVM, that's not super stable. You get new opcodes in every and then, but we have like some formal specifications. And then there's all of the cryptography. So you obviously start with the actual circuits and virtualization, and then you have the prover and the verifier that's on chain. And for these, we also have specifications, but they're really, a mix of papers and a mix of code, which are both quite informal from the point of view of a form verification. And so something that we actually need to figure out to be able to verify that the implementations are actually correct is first actually have kind of formal specifications for the entire stack, which is something that, especially for the kind of cryptography, we don't really have yet. It's something that's we're starting to work on, and that in maybe even kind of early 2025, we'll have some early results on that, on trying to formally specify some of the polynomial commitment schemes and some of the polynomial IOPs, so that then we can actually look at the code and verify the code against these specs in the same way that we're going to verify maybe REVM against some of the existing EVM formal specifications in K or Lean, and in the same way that we have existing semantics for RISC-V. And so we can, look at a RISC-V ZKVM and check that, the CPU that the VM is supposed to be is actually a RISC-V CPU and not, something else entirely, in which case, who knows what's going on there. So yeah, we do definitely want to look at the actual implementations, make sure that the implementations are correct. But for that, we need obviously to have all the specifications in place to be sure that what we're checking is the right thing.
Right, and my understanding is that not only you need the specification, you need that specification to be converted into something Flynn would understand, right? So like I assume RISC-V. I'm not very familiar with RISC-V, but I understand WASM very well. I assume they at least on a very high level, similar, right, to an extent. Yeah. And if I'm thinking of proving that a particular implementation is correct against WASM, right, that means that I need to, within Lean somewhere, I need to effectively implement the whole WASM transpiler, or rather virtual machine, so that Lean understands what particular WASM code would be doing, right?
Yeah. So you need to have those semantics in place. And the nice thing with RISC-V there is that there are actually official semantics that are maintained by the main RISC-V project, and these are written in a specification language called Sail, which is developed by a bunch of people in kind of primarily Cambridge. And from Sail, you can get extractions into serial provers like Hall, Coq, Isabel, and as part of this project, we're also getting an extraction to Lean. And so once we have those semantics that we can get into all of the serial provers that we'd like, then actually what you can do is you can take a specification of an optimization, let's say air, if you wanted to have a Stark-based EKVM like many of them are, and you can show that the optimization you have, it will be an encoding that preserves the semantics of the virtual machine. And from that, you obviously get a sense that whenever you're trying to prove some execution trace of that virtual machine, the semantics are correctly encoded, and therefore what you're proving is actually what you think that you're proving, which is quite important if you want to avoid having either kind of proofs of programs that don't make sense, whether that's trying to prove the execution of programs that haven't actually been executed, or whether you do actually execute something and you're not actually able to prove that you've done so. Both of these would obviously be very problematic.
Yeah, that sounds. I never heard of Zale before. That sounds very exciting. I don't know if there's something like that exists for WASM today, but that would be.
You would definitely be able to write a WASM specification in Zale. I don't know if there is one, but I think WASM has been pretty good at having somewhat of a mathematical specification, so it shouldn't be that bad. It would be worth looking into it if you're trying to formally verify a bunch of things and using WASM. Then I think it would be worth putting a bit of effort into it.
Yeah. So an interesting thing about ZK zero knowledge in general, or I will go even a little backward. So when we were building back before we launched it, we had a very good cryptographer in our team, and every now and then I would be and actually building a blockchain builds a fair amount of cryptography, and I was never an expert in it, but I have some like layman understanding, and it was fascinating always when I would be pretty certain that something that I think is correct, I would bring it to the cryptographer on the team, and he would completely destroy it, and he will show me ways where my construction breaks, right? And with zero knowledge, with ZK, the problem is that the cryptography is even more complex than like hypothetical, like signatures or like basic things we use, like key generation, BLS, which are somewhat easier to understand for a person. And I was always fascinated with the fact that, like, maybe in the whole world, there's like maybe low hundreds, if even that many of people understand ZK sufficiently well to actually reason about it, right? But we put so much trust in it, and from this perspective, obviously, if there was proof, like if there was an assertion or like hypothesis saying, under those cryptographic assumptions, the information will not be revealed, and then the proof you don't need to understand, right? The beauty of Lean is that if you understand the hypothesis and the code compiles, you know that the proof is correct, right? You don't need to understand it. I think that would significantly increase the applicability of zero knowledge technology in general to many use cases, right? Because today we effectively trust people, who think at a level that is way beyond my comprehension, for example, right? Because they said, "Trust me, I'm a corgi." That's the correct instruction, right? And similarly, implementation-wise, I remember there was a bug in Zcash back in the day that was found by someone, right? But Zcash was built also by tier 1 people in the industry, right? So they missed that like something wasn't zeroed out. So I think those are really important.
Yeah, I think the bug in Zcash, if I remember correctly, like came from an actual typo in the paper with one of the superscripts. Like one of the superscripts to indicate like the group element, there was just one typo and then it just destroyed soundness. And you've had kind of quite a few vulnerabilities, I think, especially not even with the kind of proof systems themselves, but even with the circuits. There have been quite a few examples of under-constrained circuits showing up in testnets and devnets, and for all you know, maybe there are some in mainnets, and you only need, one unconstrained variable, or one line somewhere that lets you mess with memory, and suddenly you lose soundness for your proof system, and everything breaks. And because one of the really nice things that's I think going on in this industry is that we're quite good at taking brand new research and deploying it into live systems in maybe like a year or so. That's quite exciting, but it also means that there's very little time to actually check that things really work the way that they are. And also, once you go from papers to implementations, if you look at the proof systems, you can look at the paper for Starks by the Starkware team, and it's a really good paper. They're all really smart. Is probably correct. But then you look at the implementations, and suddenly you don't have just one Stark, you have recursive Starks, and you suddenly need to make sure of does that change your assumptions? Is your security parameter the same? Do you have the same amount of bits of security for all of these proofs that are recursive? And suddenly, now I think as of this year, Alexander Hicks and some of his quarters have a paper that came out related to this, and this is kind of a few years after we've already had Starks in productions. And so because there's that lag between the high level details and the protocol specifications on paper, and then implementations doing some innovation as well on their side to actually make things work in the real world, and then Siri catching back up to those implementation details, I think form verification can play quite a useful role in figuring out where we have gaps and where we have things that we don't understand. Because if you're trying to formally, prove that, code implements some kind of specification, then you quickly realize where your understanding is lacking and where your security model might not actually, apply to the real world code that you're looking at. So there's very kind of practical aspects to this as well. And that I think that adds to the feedback loop between the innovation on the research side and the innovation on the implementation side. And if you do it correctly, I think to some extent it means that you can possibly push performance even faster, because if you are formally verifying things and you're getting, correctors as part of your development cycle, suddenly you can do, the sketchiest looking optimizations at every step, but they're formally verified, so it's okay. And that's something that I think hasn't been done in our industry, sadly, but it's something that, for example, the form verification team at AWS does really well, where they will get, 60%, 100% improvements in performance on things like electronic signatures or access control within the AWS stack. And that pays off to a very large extent because they're serving, hundreds of billions of requests maybe per second with the size of their stack. And their experience has actually been that once they set up the whole process of form verification as part of development, they've actually been quicker at getting new code out and better performance out than they were before formally verifying things, because actually now they can move faster with correctness along the way built into the development process, and therefore ship faster and get performance out faster. And I think for us, if we could get the same for all of the proof systems that we're deploying, then potentially we could accelerate things, even further than we're doing now, and that would be very exciting.
And so let's for a second assume that artificial intelligence does not become good at helping with proofs and whatnot, right? So what would be the strategy? Would you be trying to recruit people who already understand Lean pretty well, or what would be the approach to having this machine that keeps on proving the new code, new changes?
Yeah, so the approach now is essentially to have a big budget and to try and get as many people involved to do this. For two reasons. One is obviously that the scale of the work is really big. One ZK VM by itself is a really complex stack. And then in practice, actually, we have several ZK VM teams that are all doing good work, right? You have Nexus, Succinct, RIS0, Jolt, Powder, and there'll probably be more coming up. And so we actually need to kind of hopefully make it possible to verify multiple of these ZK VMs that have different implementation details and different optimization techniques. So we want to get a lot of people involved because of the size of the stack, but also so that actually as many people as possible within our ecosystem have hands-on experience with that kind of work. If you rely on a single team or one or two teams that are, maybe particularly good, they also only have limited time and that'll make maintenance impossible across kind of multiple ZK VMs. But then, there's a lot of effort that goes on into trying to plan for maintenance, and that's something that's occupying my brain quite a lot these days. It's not always clear how to do this because teams want to ship really quickly. They want to, write a new circuit that's a bit more efficient and deploy it. And if verifying that circuit takes a couple months, and then by the time you've done that work, they actually have a new circuit ready to ship, the code that you're running is never the code that's actually formally verified. So for maintenance, we need to figure out ways to embed form verification into the development process. And that's about building relationships with developers and the kind of form verification contractor teams that exist, and better tooling, right? If we can maybe start writing circuits in Lean directly or some kind of Lean DSL instead of writing them in whatever Rust-based DSL, maybe we get people just write circuits that are just kind of fairly easily provable in Lean. And things are better, or maybe we just build better tooling to extract circuits from Rust or Noir or Circom or Cairo and whatever, extract these into Lean, and then maybe build some automation in Lean to verify these efficiently. That's something that we're actively working on. It's not something that has easy answers, unfortunately for me, but it's something that we're putting a lot of effort in, and that's part of the reason for having such a big budget. Is that the goal really isn't to verify, one ZK VM once and then, hope for the best in the future. It's to make sure that we put everything in place sort of beyond the 2-year lifetime of this project there's a path to maintainable form verification for multiple zkVMs that can be sustained by the zkVM teams, themselves, hopefully, because they're all keen on obviously having form verification done on their stack. And if we give them the tools to do that and show that it can be done, efficiently in terms of time and costs, then I think we're set for a better future in that regard.
Yeah. And I want to get a couple of estimates from you, from your experience, right? So let's say, like as a unit of measure, let's say there's a piece of code that took, let's say 1 week to implement. So in your, like on a very, what would be a very rough estimate in terms of how much time it would take to write the assertions about it, right? Like the things to prove, and how much time would it take to actually prove them?
That's a good question. I don't think there's a standard answer, because you could write code that is fairly easy to prove. For example, if you don't have any weird optimizations, one thing that often becomes a big time sink is when, someone might go and see a contractor to do form verification on some code base, and the code base might be implementing a proof system, or maybe like just a smart contract verifier, let's say. And that's a fairly small amount of code. It's not insane like an entire zkVM. And it might not take that long to write, but it might include a lot of optimizations. And then the tricky part there is that the form verification team gets given this smart contract written in maybe YAML that has a lot of optimizations. And the question of correctness doesn't just become, is the actual specification for the verifier correct? It becomes, are all of these optimizations not breaking the correct specifications of verifier? And so it depends on what you're given, right? If you're given an optimized smart contract, it's really hard because you have to reverse engineer essentially all of the optimizations to figure out like the kind of base unoptimized program that should match, the specification for the verifier that would be maybe in the paper or in some kind of documentation. And that can be quite annoying and tedious. But maybe you're given unoptimized code, the optimized version of the code that, has some easily shown link with the unoptimized code and a nice specification, and then your life is much easier. So yeah, I don't think there's a good kind of standard estimate of how hard it is to verify things, because a lot of the times what happens is that actually the problem is not so much in the verification itself, but in the varying levels of specifications that you start with, and that has a big influence on figuring out what you're supposed to do. And similarly, sometimes you start with no specification, and then you have to figure out a specification, do essentially a manual audit of the code to figure out what's going on. And that can, we all know audits take, a lot of time. So a lot of the complexity is not only in the verification, it's also in figuring out what the handover from developers to form verification teams looks like, and how kind of the relationship exists between these kind of two different teams that have different assumptions and different goals about the system.
But would it be fair to say that first, if you already have a proof for a non-optimized version, it would be easier to prove the optimized version, right? Because you can probably just reduce it to the non-optimized version, right? So an iterative development. If proving the implementation was always one of the CI checks, right, then you have a lot of things you can tap into, right? You have a library of hypotheses and proofs that you can take advantage of.
Yeah.
And, go ahead.
Yeah, it makes if you have in an ideal world, you have a formal specification, you have a non-optimized implementation of that specification, and then you show that that implementation matches the spec, and it's easy because it's optimized. And then you have an optimized implementation, and you show that the unoptimized implementation behaves the same way as the optimized and non-optimized implementations behave the same way. And that means you don't need to relate some weird optimized implementation to a specification where it's clearly not obvious that they're the same. And that makes your life easier. I think it also probably helps you with automation. A lot of goals, if you can use SMT solvers and things like this, you can gain a lot of time essentially just brute forcing through a bunch of assertions. And that's always easier with an unoptimized implementation that clearly matches the formal spec that you're working with. So yeah, I think a lot of work should just go into specification more than anything. If you like, a good specification is very close by itself to a formal proof in a sense. Once you have type checking and everything, it's really close to the same thing.
Yeah. And so going back to artificial intelligence, right? If we remove this assumption that artificial intelligence does not become good, a couple interesting things that we've been doing. One is generally I've been thinking a lot about formal verification, not from perspective of ZK VMs, also from perspective of ZK zero knowledge, but more so from perspective of generally building smart contracts, because smart contracts without formal proofs do not quite live to the promise of blockchain, right? If I'm not experienced enough to verify myself the implementation of hypothetical, compound or Uniswap, I'm always taking chances, and I'm still trusting a centralized entity that built the code, right?
Yeah.
But if there's a formal proof, and I can only need to verify the assertions, it's still possible, obviously, to mess up the assertions, right? Like that will always be. There's always going to be some human factor. But it's much easier to review the assertions, right? And then say, oh, indeed, if I put my money into this Uniswap, like the product of the pool will not change, etc. Right?
Yes.
And from this perspective, one effort I've been quite involved is I don't think Lean or any of other implementation is. I think they all designed so that good actors are able to share proofs with each other, but they're not necessarily designed against a bad actor that tries to build a proof that breaks it, right? So presumably, I'm pretty certain that a bad actor would be able to prove false Lean by like triggering some overflow or something. Right.
So you can also, if you're a bad actor, it's you can add an axiom that you would like, and then prove whatever you want based on that axiom. So you have to be careful.
But that you can check, right? Like axioms and sorry.
Yeah.
And like the red flags you can definitely check for. But there was a website, I will never remember the website, but they had like a list of ways in which like type safe languages were broken because of the implementation bugs, right? And in the actual usage of Lean, it is not a problem, right? It is very unlikely you would trigger any of those accidentally. So like, if mathematicians share proofs, or if people who build ZK VMs share proofs, they're probably not malicious, hopefully not malicious. But if you put smart contracts, that's it's a different story. So I'm working on a way less capable but much simpler formal system, and I'm launching before the end of the year an effort on at Near we have a annotation platform where we annotate a lot of coding and math data, and so I will be annotating a lot of formal, or like building formal proofs for code. So that will be like a step towards training those systems. But I don't think we would be able to annotate the sufficient amount to make them good, right? So something like alpha proof would be necessary, where machines do it themselves. And the beauty of the formal verification systems is that the proofs, there's an explicit reward, right? The proof is either correct or not, and when it is correct, you get the reward. And the proof is the most complex part of the process, right? So like writing the hypothesis is like a small percentage of the work relative to proofs, right? And that's something that I think alpha proof is a great example of the fact that it's possible to use reinforcement learning to do that.
Yeah, and I think because alpha proof was doing something really interesting as well, which was that they would auto formalize the IMO problem statements with a fine-tuned Gemini model, but then they had this whole reinforcement learning loop where you would take whatever statement you were trying to prove, and it would actually generate, thousands of variations of that statement, most of which are then false. And that would give a lot of related training material to their model. That some of it is quite simple, because some of these things, you change, one symbol in the same statement, and it's obviously wrong. And so that's very easily solved by the model. And then not only do you learn how to prove, statements that are true, but you also learn how to show the statements that are wrong or false. And that probably prevents, I think, a lot of hallucinations and other kind of issues that you would run into with, if you're trying to generate kind of regular code that's not formally verified.
Yeah. When you write a intermediate hypothesis and that immediately says, no, that is not.
Yeah.
That is not the case, and you're not wasting a bunch of time by proving something that was based on it. That's pretty helpful. There's also an interesting thing in there. I don't remember where I read it, but they were mentioning that they have a process of formalizing the statements. Right? They begin with a bunch of math problems from Chinese Olympiads, but those are written in natural language, so they have an auto-formalization process that they don't go into the depths about. But they mentioned that, sometimes it fails and doesn't transcribe it correctly, but it doesn't matter. As long as the problem can be solved, it is still a good data point.
Yeah. It's interesting. So I know I've tried using Claude to auto-formalize, some serious statements doing cryptography papers, and sometimes it fails in quite interesting ways, where one thing I've seen happen kind of a few times now, just running experiments, is that you'll give it a statement of a theorem that says, there exists some unique X such that, Y is true. And it'll usually formalize the there exists X part well, but sometimes it'll miss out on the unique part of there exists a unique X. And you have these kind of subtle things where if you're generating training data for a model, that's basically fine. But if you're trying to generate, proofs for an actual kind of cryptographic system, then you want to make sure that the statements you have are the correct statements and not some variation, because sometimes there might be two variations that are true. It's just a weaker one, and you have to be quite careful with these things. I remember they definitely had human oversight on the auto-formalization process, which was interesting to see. And I'd love to see the statistics they had on the error rate there.
Mm-hmm. Yeah. So on our end, as I mentioned, we will be using a lot of humans to annotate auto-formalization and then building proofs. But it's not clear yet if that amount of data will be sufficient to have any meaningful results. That we will know in maybe half a year when we have a reasonably big chunk of data annotated and start fine-tuning. I'm pretty hopeful, but it's with how data hungry models are, you never know.
Cause I think there's one thing that you can do to maybe be a very interesting test case is you have all of these annotations, you have a few languages which aren't lean, but you have language like Daphne or Quint, which was developed by the Cosmos team. And these are just kind of specification languages, but they have some automation built in for property testing or model checking and things like this. And so you can kind of test, your extraction from Solidity code or your code or, whatever smart contract language you're using to these languages to the extent that you can just prompt an LLM, get a translation, and then do the automated model checking and property testing and or fuzzing and see if something breaks very quickly in that sense, and potentially feed that back into the training process. And that'd be quite interesting, because I think especially for Daphne, you have some non-AI based extractions from Daphne to Python and from Python to Daphne. And so if you want to, you could start generating a lot of Daphne code and a lot of Python code, and then do the kind of non-AI based translation between both, but also train a model on all of these translations and potentially get quite a lot of training data out of that.
Yeah, that sounds like an interesting idea. Yeah, generally any synthetic data is obviously better than human annotated because it scales.
Yeah.
So another interesting thing you mentioned at the very beginning is, if you swap, instead of finding ways of using AI for formal verification, how can we use formal verification for AI? And I never thought, to know that the model is doing what you think it's doing, right? And I never thought of formal verification from this perspective. But one interesting, I would like your thoughts on the idea of there is on the latest NVIDIA GPUs on H100s, they have what is called trusted execution environment, like effectively what TDX is on Intel, right? and we are contemplating the idea of training a large language model inside the TDXs, so that you know that the model is actually the output of a particular code run on a particular data, right?
Yeah.
So that you have a large language model like a 500 billion parameter model for which you have a proof up to NVIDIA being honest that the model is the output of a particular code and data, right? So I wonder if you think that is sufficient for the requirements you have, or if this is not quite there yet.
I think it's such a complicated question because I feel like a lot of the terminology around AI and transparency and decentralization and things like this for AI isn't fully fleshed out yet. And so I think to some extent, if you get, you train your model inside a trusted execution environment, and then you get some certainty that at least there hasn't been bugs during training. That's what you kind of get out of the box. But then to some extent, if the data that is trained on is trash or, heavily biased in some intentional way or something, it might still not satisfy, your requirements you would have as a user. And to a large extent, I think bugs during training isn't something I'm massively concerned about, if only because neural nets are quite robust to noise. So this is, if you had a few bit flips during training because of a solar flare or something, your model probably wouldn't change that much. And so that's less of a concern for me. I think a lot of the concern for me, and this is purely from me as a user and not me as someone who would train models, whereas you're thinking of training models, is that, for any model that you use, even if you're running it locally or you're doing, inference with a ZK proof that, the output you get is from the model that you expect, it's really hard to know. It's impossible to know what's actually in these models. And even, what the system prompt is sometimes, and therefore how the model is going to behave regardless of the data that it's been trained on when you set it to do a task. And sometimes it's very easy to test, right? If you had an AI agent and you tell your agent, I want to order a stainless steel pan from Amazon, then, you can check what comes in the mail 3 days later. And you can check that it's a stainless steel pan and not a cast iron pan or a non-stick pan or something else. But if you were saying hey, give me some explanation of this event, then it's really hard to check that explanation is correct. And maybe there's not even kind of a nice sense of ground truth for it. What you'd really like to check is whether, there's some kind of bias in the model that isn't breaking rules of common sense, or your own rules of common sense maybe that you would define for yourself and things like this. And I think that's where a lot of what I'd like to check with respect to models and my use of them is to figure out whether I can define some basic common sense and check that the model follows that basic common sense to some extent. And I think that's really tricky, right? It's kind of like defining a really good system prompt and making sure that the model actually follows the system prompt and maybe didn't, jailbreak itself or something like this. So it's a really, but I think it's a very open question. I don't think there's any clear sense of direction of how to kind of solve these questions, if only because of the complexity of the models and things like this. And it ties back into all of the questions around, mechanistic interpretability and all of the research that's going on there. But I really see it as something that's not a kind of, safety thing, let's not hope the AI is killers or something, but something that's actually for the kind of day-to-day user experience. If we are going to start using AI agents to execute a lot of tasks day to day, then it starts becoming very important, I think, to get a sense that the agents are actually doing things that conform to your common sense, and that it's not some agent that is encoded some bias or common sense from some, open AI and then feeding that, back into you. If you're, whatever, trying to analyze data, analyze news, trying to generate, secure code according to some specification or things like this. And I think that's quite exciting and something that maybe is a bit under discussed in a lot of talks around transparent AI and decentralized AI and user-owned AI, probably because there are no good answers at the moment. But I think it's really interesting to think about what that would even entail.
Yeah, I have no good ideas in terms of how to do that with the formal verification, because the model is very the model is an alchemy. Right? It's not like a well understood process. But in terms of to address your other concern, it's with keys. My understanding is that you can have in the future, like the attestation, you can run the process in such a way that in the future you can prove that the output is the result of a particular computation, and therefore you can start by saying, well, we're going to start with the like common crawl dump, that goes all the way up to mid 2020. When was the ChatGPT? Mid 2022, right? And then the whole data preparation process, the whole model training process are open source, and there's a commitment. There is a proof that they were used to train the model, right? So then that at least intentionally, unless someone was smart enough to put something, into the common crawl before 2022, then at least intentionally the model is not trying to deceive you, right? So that's at least like part way there in terms of solving the problem.
I think that would help a lot. But I think there's also saying like a lot of some terminology around what open source AI is in terms of does it mean open weights, does it mean open data, is still kind of so maybe kind of either misused or confusing, that it's hard to always be super specific in terms of what you mean, and that makes it hard to evaluate a lot of things. But I think if you get to the end-to-end thing where what data is trained on, that it's a kind of standard data set that people have looked at to some extent, right? Obviously, if the data set is insane in size, it's not like you won't be able to really audit it. Then that would obviously like help quite a lot, I think. And hopefully we start seeing this, because one of the things is you have Llama 3 now is what people think of as the epitome of an open source model, but in practice it's trained on a lot of proprietary Facebook data that we'll never see and never understand, and that always kind of makes me slightly uneasy from that perspective.
Yeah. So something I like about it. So as I mentioned, right, for the raw data, you will need like on the order of tens of trillions of tokens, right? So nobody will review in any meaningful way tens of trillions of tokens, but they can review the data pipeline, right, and the inputs, and say, well, okay, as long as we believe that those inputs are actually common crawl, and we have those beliefs about the common crawl, then that resulting data set has the following properties, right? But for the fine-tuning data, I think an interesting approach here is you can define a process, like you can, as I mentioned, we did a lot of things around data annotations, and you can define data annotation like checks and balances, the whole protocol on a smart contract, run the whole annotation on a smart contract. So now you know exactly which participant participated in annotating data, what was the review process, what were the guidelines for review, right? So you can have certain estimates in terms of how much malicious data was able to sneak in through, during the preparation of fine-tuning data. So there's a lot of interesting ideas there around, what sort of guarantees we can provide.
Yeah, I think transparent annotation would be a big step. That'd be very cool to see. Yeah.
But yeah, it's a bit of a deroute from formal verification, but there's a lot of interesting ideas there that.
Yeah, but I think to some it's a bit of a deroute, but I think it's in like it's not like I think formal verification is some silver bullet that will solve all of these problems. I just think it's a useful framework to think about these things, because it forces you to think of trying to define things properly and trying to figure out ways of understanding, what different things imply and how to reason about them. And so from that perspective, I think it's always useful to keep in mind. But obviously the kind of the complexity of everything will always make it hard. But then if maybe if you get actual AGI, maybe the AI will figure out how to formally verify itself. Who knows?
Hopefully. Yeah, that would be if it is possible at all, eventually it should be able to do so.
Yeah. Yeah, it'd be nice. I think, a test case of if you ask it to generate, a bunch of Python code, can it generate a proof that Python code is, matches the specification you asked it to generate? And I think this is something that people are actually working on. I was at a workshop in Cambridge earlier in October, and someone did actually bring this up, that, now that people are, getting a lot of code from prompts, then instead of prompting, Claude or ChatGPT for some Rust code, you should prompt Claude or ChatGPT to generate some code in a specification language that you would then design for that purpose, that would then be extracted into, Rust or something like this with a verified pipeline. And I think that's, one maybe practical way of addressing these things is developing the tooling such that instead of, getting an output that's directly from your prompt to Rust and hoping that the AI can formally verify this, actually what the AI outputs is a formal spec of what you asked for, and then from that you generate, Rust code that matches that specification, and that suddenly becomes actually quite a practical goal and something that's well within, well defined, that you can give to form verification experts to work on, and all you need is to actually design that kind of specification language that the AI returns as the output of a prompt, and hopefully that kind of makes everyone's life easier to get formally verified code.
Yeah, it's very on the lines of what I think when we were starting Near AI with Ilya, one of the diagrams we had was, user talking to the AI, but the AI is not solving the problem yet. The AI is building a formal specification of the user request, communicates it back to the user until the user says, yes, that is exactly what I want, right? And then everything comes from the symbolic space, and you sort of know that what you get back conforms to the specification that you and the agent, devise together, which I think is interesting. Yeah, I think it's very similar to what you're describing.
Like I think everything that's going in that direction is really useful. And I think, if you're talking about code, it's at least possible to start reasoning about, specification in some formal sense, right? It's when you move to, other things that are based on common sense, where it's much harder to define that in a formal way. And because everyone has, their own personal view of what common sense might be, and their own biases that they think are correct. And that's something that's, the next level once we figure out, generation of correct code, I suppose. Yeah.
Okay, we're slightly over time. So as the closing thoughts, so if people, there are probably people who are interested in formal verification or, in application with ZK EVM. Where do they go, to get involved?
So the verified-zkvm.org website is a good start. And then my email is listed somewhere on that page, and that's a good next step after that. We've got a lot of people involved. We have one big Telegram channel with 140 or 150 people who are kind of interested in the project, and obviously for some of them participating in getting funding to work on this. So anyone that wants to have a look at contributing and want to follow things more closely than the documentation that'll be posted on the verified ZKVM website, can send me a message, and we can go from there, and they can get in touch with everyone.
Awesome. Okay, that was a very exciting topic, and thanks a lot for joining us today. And
thanks for having me, and I'm looking forward to the 500 billion parameter model that you will train. That'll be fun.
Yeah. Okay.